let's move to the second part, surface and dislocation diffusion from experimental observations. So first of all, we are going to talk about the diffusion along one-dimension dislocations. So as you learned before, one-dimensional dislocation, when an atom at one-dimensional dislocations has a higher energy, so that will result the lower activation energy. So that will help atoms diffuse through one-dimensional dislocation faster than that inside the grain. So the concept will be similar with what we learned in grain boundary diffusion. And dislocations are fast diffusion channels leading to diffusion tails in solid. What this means? Dislocations are fast diffusion channels, as we mentioned before, because when an atom at dislocations, it has higher energy, so that will result lower energy barrier, so the diffusibility will be higher. So this can be considered as a faster diffusion channels inside your materials. And so when your samples have some one-dimensional dislocations, so what the concentration of diffusing atoms as a function of penetration depth. So what we have here is we have a substrate, and we also deposit a diffusion source on the top of our substrate. And inside this substrate, we observe there are several one-dimensional dislocations perpendicular to our surface. So it will be perpendicular, right? So when diffusion happens, you can expect that the diffusing atom can diffuse through the substrate, but because there are some faster diffusion channel on the dislocations, so that some atoms will diffuse through these dislocations and move faster than that inside the grain. So when you try to plot the low concentration as a function of penetration depth, you can observe interesting curves show like this and can be fitted by two straight lines. The first straight line would be correlated with bulk diffusion or grain boundary diffusion, and the second straight line will be due to the dislocation pipe diffusion. So as you expected, if we do not have this one-dimensional dislocation perpendicular to this surface, we don't have that. So the curve should be like this, right? If we don't have one-dimensional dislocation perpendicular to our surface, substrate surface, so the concentration should be like this. But however, due to we have this faster diffusion path on the dislocation, so you find that you can have this kind of tail, diffusion tail inside your substrate. So we can find some diffusing atom at deeper inside our materials. But instead of if you check this, if there's no one-dimensional dislocation, then at deeper region we cannot observe any diffusing atoms. Okay, so this is the solution you learn in lecture 3. It demonstrates that if we have an unlimited source, which means if we deposit a diffusion source on the top of our substrate, then the concentration profile can be expressed like this solution, based on this solution. And if you try to plot the concentration of diffusing atom as a function of depth or x, then it will turn like this. So this red curve is similar with this one, but if there are some if you have some one-dimensional dislocation perpendicular to our surface, then you can observe the curve, concentration curve will be shown like this, and with this tail, diffusion tail. Okay, so this is how you can know whether there are some one-dimensional dislocation perpendicular to your substrate. By what you can measure the concentration of diffusing atom as a function of depth. Then if you observe this tail, then you can find, oh, we have some dislocation perpendicular to our surface. Okay, and this is the experimental observations along diffusion along dislocation. But how about diffusion along free surface? Free surface, if the atoms were at the free surface, then it also have a higher energy, and leading you have a lower activation energy or lower energy barrier. So that will result the atoms can easily overcome this energy barrier and can diffuse faster through this diffusion path. So diffusion along the surface can consider as a thin slab of fast diffusion channel, and the thickness can be considered an atomic size. And why we need to emphasize or highlight the thickness? Because when you calculate or estimate the effective divisibility, you need to consider the volume fraction of for each crystal imperfection site, right? So if you have a free surface on your substrate or inside your materials, so you also need to estimate the volume fraction of this free surface. So for free surface, you know the area A, right? But how about the thickness? Lots of people ask about the thickness of the free surface. You can consider the radius or the size of the atomic these atoms. So will be the atomic size will be the diameter of these atoms. Can consider as the thickness of this free surface. So here I'm going to give you an example about to observe or visualize the surface diffusion. So this is published in 2005 by Professor Liao's group. So he deposited a thin copper film on a substrate, and here in the meantime he allowed the current passing through this thin copper film. So when he increased the current density, then as you know, when the current density is high enough, that will drive the atomic migration. So under these situations, this white arrow point out the direction of electrons flow due to the current applied on these materials. And he put these settings inside TM to in situ TM hope can observe the atomic migration during applying the current. And you can observe the fringes here, so we can identify there's a grain here, and the direction here is 0, 1, 1 bar. And he did continuously apply the electrons flow or current passing through this copper substrate. So the A, B, C, D, E, F actually means when increasing the time period. And what he observed here is you can observe a complete grain here, but when you increase the time, you can observe some portion, some region at your left bottom region, the fringes disappear, and this region will get larger and larger. You can observe in figure D, you can observe almost half the fringes disappear, right? And when in the D, you can observe two-thirds grain disappear, and in figure F, you can see the whole fringes inside this grain disappear. So in TM, if we observe the fringes disappear, which implying that what? The atoms be move away or be already leave its original crystallinity, right? So let's simulation figure and also use the same direction with here you observed in TM figures is 0, 1, 1 bar. And this copper actually in this figure simulation he used different color of atoms to represent different layers of copper. And you can observe actually let's some atoms here, and we can find that when apply the electrons or electrons flow, this atom, the first layer of atoms can move away or can diffuse through these channels along 0, 1, 1 bar. So he proposed that the mechanism probably would be due to the electrons flow pushing this atomic movement, and so these atoms, copper atoms, diffuse through these channels. So as a function of time, so finally all these copper atoms diffuse away. So we cannot see any fringes anymore in figure F. So this is evidence, or this is a case demonstrate that surface diffusion really happens on the surface of your materials, and this diffusion pattern actually belongs to an isotropic diffusion mechanism, and is depending on the crystallinity because the direction of this moving diffusing atoms actually is moved through specific directions due to crystallinity. So this type of surface diffusion, we call it as an isotropic surface diffusion. And this is an experimental observation to show you that free surface diffusion really happens. But some people also use some simulations to try to simulate or to show you how the diffusion happens on the free surface. So this is a simulation results through the interstitial seam mechanism. So it was 1 to 10 atoms here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you put an extra atoms on the top of the surface. So this is something like this can be considered as a self-interstitial defect. And this self-interstitial defect is not the one we talked about in previous section. Self-interstitial defect is the one inside the crystal, right? But here, this self-interstitial defect is shown on the surface, material surface. Okay, so this self-interstitial defect will be try to move into these materials. Through what? Through hopping or kick out. So what's the hopping? Hopping means the diffusing atom was at the interstitial side and will jump through interstitial sides. And the other kick out actually is the diffusing atom was at the interstitial side and it moved to substitutional side and kick out the atom who was at substitutional side. So this phenomenon, this mechanism actually is similar with what we learn in interstitial seam mechanism. Okay? And this is similar to interstitial mechanism, right? Diffusion mechanism. Okay, so before I ended lecture 5, so I'm going to give you an examples. So the title here will be, we hope you can calculate the grain boundary and dislocation diffusivity. So what we have here is we have a polycrystalline copper film. I draw a polycrystalline copper film with thickness L and has a bamboo-like grain structure. Bamboo-like grain structure, and diameter is D, and the thickness of grain boundary is delta. So bamboo-like, I just draw one bamboo-like grain structure, but we have more, right? I just you draw this to show you what means bamboo-like grain structure. So this is a grain diameter D, and in between two grain we have a thickness of grain boundary delta. And additionally, we also have a bundle of edge dislocation with a core diameter delta and a density rho. And it's a bundle of edge dislocation means we have lots of dislocations, and the core diameter is delta and the density is rho. But you need to focus, or you need to pay attention on the unit for the density. Here is the length of dislocation per unit volume. So the length here, it will be the total length of dislocation per unit volume. So I just try to draw 5 dislocations, and the diameter is delta, and the density rho actually is summarize all lengths together, then you will get the total length of dislocation per unit volume. This is the unit for density rho, and the direction of this dislocation are perpendicular to the film surface. It's shown like this. And the self-diffusivity of copper atoms along crystal, grain boundary, and dislocation and the surface are dxl, db, dd, and also ds respectively. So please answer following questions. So the first question is, what is the ratio of atoms diffusing through the dislocation and through the crystal? So based on your questions, so we know the diffusing atom will deposit on the top of this polycrystalline film, right? And allow diffusion happens, where the direction will diffuse go downward. And due to the materials, inside these materials, you can find the grain boundary and dislocations, and also some surface here. So the first question, I want to ask you the ratio of the atom diffusing through the dislocation and through the crystal. So here you need to learn the ratio. Actually just ask you a volume fraction, right? Because as we know, the ratio of the atom diffusing through this two means he want you know the volume fraction of dislocation inside these materials. So here is we need to learn the ratio. So is the number of copper atom diffused through the dislocation versus through the grain. And based on this, and we also divided by the dt. So actually here, you know, as long as we know these two, then we can directly use this divided by this one, get the ratio, right? And this actually just give you a hint that this for these questions you need to start from the flux, right? Okay, so the flux, what's the flux? Is the numbers of copper atom diffused through the grain per area per unit time. will be expressed like a minus diffusivity dxl concentration gradient, right? So this is for this one. And the other one, in order to get the numbers of copper atom passing through this location, so also we use the concept of flux. So the dt and also AdL is the area for this location, and this one actually is the flux JD along this location. And JD actually you can use the minus dd diffusivity along dislocation concentration gradient. But regarding to the area dislocation of area, some people probably were a little bit confused. So here I forgot to point out the A actually is the area for the substrate A, because the diffusing atom actually is deposited on the top of the substrate. So the area, diffusing area for this one will be A. Okay, and how about the dislocation of this, the area for of dislocation? So you can find that in this case, actually, it just want to hope you can know the area ratio of dislocation or volume fraction of dislocation inside these materials. But if the one you just familiar to answer that would be, if you familiar to deal with the volume fraction, so you can write this down: V dislocation divided by V equals to AdL times L thickness divided by A times L. A times L is the volume of these materials, and this is also the volume of dislocations. So if you delete L, so you got the AdL divided by A. Or you can just ignore this relationship, because you can directly from volume fraction equals to area fraction for this case, because the diffusion model in this case can consider as a two-dimensional diffusion case, right? Because we just focus on this diffusion along this direction. Okay, and okay, so and the one we don't know actually is the AdL, right? We want to answer what's the AdL. Okay, so here we know the relationship between the volume fraction and area ratio or area fraction, and here volume fraction. So actually the questions give you a hint regarding to the density. So the density though actually is a unit volume length of dislocation per unit volume. So length, so you times the area, so you will get the volume fraction of dislocation. So we use the low to times the area of dislocation, then we can get the volume fraction. So based on this equation, you can get the AdL equals to dou area times the A. So be a low A area of dislocation, low A area of dislocation. Area, because the diameter is delta, so it's a pi r squared. R is the delta divided by 2, so we got square. So here we get here, and you have this one and this one. You just directly divided this equation. You just did directly to divided this equation by this direction, so we can get the number. This divided by this, you can get the numbers of copper passing through diffuse through this location divided by that through the grain can be equals to this, can delete this one. So you got a dd divided by dxl. And A, we delete this one, so we got low pi delta squared divided by 2. So this is the ratio of diffusing atom diffused through this location and through the grain. Some people probably will ask about here, this is grand, but here we use the A. Why we didn't use why don't we just use, we should use A to minus the area of grand boundary and minus the area of dislocation. Why don't we do that? But in most of case, the violent fraction of or area fraction of crystal imperfection size is quite small. So usually in this case, we just put the area of whole substrate as we can use A to do this kind of approximation. We can ignore the area concentration from, or area, or we can ignore the area of crystal imperfection side here, okay, because they are too small. Okay, so second question is, what is the expression of effective self-diffusivity in the direction perpendicular to the film surface? So effective, in order to get the effective diffusivity, so you need to know the area fraction for each crystal imperfection side, right? But here, the effective diffusivity, they point out, it will be the direction perpendicular to the film surface. So under this situation, we don't need to consider the ds because the contribution from the free surface one will be parallel with the surface, nothing related to perpendicular to a surface, so have no contribution. ds has no contribution to the direction perpendicular to a film surface. So effective diffusivity can express like the dxl times the area fraction of grand, and dd times the area fraction of dislocation, and dB times the area fraction of grand boundary. So regarding to previous slide, we know that the violent fraction or area fraction is can be considered as the area fraction, can express like this. Here we use a two-dimensional one because we mentioned that, so you just copy this value, area fraction times dd, and because we talk the diffusion pattern belongs to two-dimensional one, so in this case the area fraction will be d plus delta squared minus d squared. This will be the area of grand boundary divided by area of grand, so d squared. Then if d is much larger than delta, so you can get 2 delta divided by d put here. So this is the effective diffusivity. And regarding to the dxl part, you just use 1 to minus the area fraction for dislocation and also from the grand boundary. And the third question actually is, what is the minimal dislocation density such that the contribution of diffusing along the dislocation is compatible to that along the grand boundary? What this means, the contribution of diffusion. So this is a contribution of diffusion along the grand boundary. Dislocation will be this part, and this is along the grand boundary. This two has compatible. The contribution is compatible, means this one equals to this one. So we can get the law can express like this. Okay. We just simply move this to a right-handed side and put all the parameters inside. Then after calculations, so we can get the law can equals to this 1.02 times 10 to 12 per centimeter square. And the last question is, if the copper film is a single crystal, that means that there's no grand boundary inside these materials. How can you determine the value of dd experimentally? And also we assume the ds much larger than dd, much larger than dxl. So we don't have the grand boundary part. And even dd is much larger, but because we consider these directions perpendicular to the free surface, so the only one we need to consider will be the dd and dxl. And we also know dd is much larger than dxl, so this can be considered as a region C, right? Although in region C actually it's a dB dominate, dB much larger than dxl, but here instead of dB we use dd, so the idea would be, the concept would be the same. So we just deposit a layer of copper isotope on the top of our substrate. Then we measure the accumulation of the isotope at the other side, backside of the substrate at different time points. So actually the deviation will be the same. So the only one you need to know to get the dd would be the thickness of your copper substrate, copper film, and correlation. So correlation factors, and the most important is at different time points you need to know the concentration or the area concentration of copper isotope change at different time point. Then you can fitting that you can get the average to get the change rate in the isotope copper per area per unit time. So you can estimate the dd. Okay, any questions here? And one thing I want to emphasize, because this is a dislocation, so you also need to put the area fraction or area ratio for dislocation. This term actually is the one we just show you, the area fraction or area fraction for dislocation. So as long as we know the thickness, the density of this dislocation, delta is the okay. So delta also is the diameter of dislocation, and also we know the concentration of diffusing atom before diffusion happens or on the surface. Then we can estimate the dd in this case. Okay, so I'm going to give you a summary here. Crystal imperfection size included the one-dimensional dislocation, two-dimensional ground boundary, and free surface are fast diffusion channels. Okay, and due to the atoms at this crystal imperfection site will have higher energy, so that will lead to lower energy barrier, and which can help the atoms overcome this energy barrier that can drive the diffusion happens. That means the diffusivity will be faster in this diffusion path. The apparent diffusivity or effective diffusivity, you need to must consider the diffusivity, corresponding diffusivity and its fractions of crystal defect for specific diffusion path. So the different crystal defect for sure will have a different activation energy. Okay, so we ended the lecture 5 here.